All right, kicking off the second half of the trig unit, we're going to take a look at identities. Now, identity looks like a scary word, but all it really means is an equation that is always true, at least for values in the domain. Some of these identities we've actually seen before. You would have played around with this one in geometry. Tangent is the same as sine divided by cosine, at least as long as cosine isn't 0. You're still not allowed to divide by 0. That is always true. Tangent is always the same as sine divided by cosine, which is what makes tangent so useful. These other ones are going to be new. Reciprocal identities, keep in mind the word reciprocal, fancy way of saying flipped fraction. The reciprocal identities we've never written out, even though we've used this idea. Remember the very first day of trig, we were able to take sine and then just flip the fraction to get cosecant. The same thing for cosine. I could take cosine and flip the fraction to get secant. Last but not least, tangent, we were able to flip that fraction and get cotangent. Those are called reciprocal identities. So more formally, I can say that sine is just 1 over cosecant. Cosine is 1 over secant. Tangent is 1 over cotangent. Now, outside of the numerical cases from the first half, we don't usually use this version of the reciprocal identity. Usually what we want to do is turn cosecant into 1 over sine. We want to turn secant into 1 over cosine. We want to turn cotangent into 1 over tangent. The reason we usually use that second column is because we're more comfortable working with sine, cosine, and tangent, our geometry functions, than we are with cosecant, secant, and cotangent. Last but not least, we get our Pythagorean identities. It's worth noting, you see these little 2's here, that's a shorthand notation. The reason we put the square next to cosine like that is because it would take extra parentheses to write it this way. When you see cosine squared of theta or sine squared of theta, what that really means is you're squaring the whole function. So that's a shorthand notation to avoid using parentheses. So why we call these Pythagorean identities? Because they come from the Pythagorean theorem, that a squared plus b squared equals c squared, remembering that 1 squared is just 1. So let's go ahead and start using these things, because at first glance it's like, holy cow, lots of stuff. But some of these problems really aren't too bad. So what happens in the middle of an algebra problem, maybe you multiply both sides by something, divide both sides by something, you might wind up with more than one trig ratio in the same expression. To simplify means we either want to get a single function or a number, something like 1 or 2 or 0. That is our goal, to turn lots of trig into either one trig function or just a number. We did the same thing with logarithms a couple chapters ago as well, where we try to condense logs into a single one. So one thing we always want to look for is trying to turn things like secant, which I do have here, trying to turn things like secant into cosine, or cosecant into sine, or cotangent into tangent, using a reciprocal identity. So the reciprocal identity I'm going to use in this case, I'll go ahead and clear the whole screen. The reciprocal identity I'm going to use here will be that one. It's always helpful to turn cosecant, secant, and cotangent into sine, cosine, and tangent because we are more comfortable dealing with those. So I'm going to substitute 1 over cosine in for that secant. Well, now it's helpful to see, I'll rewrite that sine of theta as sine of theta over 1. I can just multiply across. Sine of theta times 1 is sine of theta. 1 times cosine of theta is cosine of theta. And, I wonder if I can simplify that. Sine over cosine. Oh, look, that's right here. Sine over cosine is the same as tangent. So I have turned 2 trig functions into 1 trig function. That's what the goal of simplifying is, to turn lots of trig into 1 piece of trig. Let's do another one. Taking a look at 5, I now have tangent and cosine. Well, neither one of those is one of our reciprocals. We don't have for example, we don't have cosecant, secant, or cotangent here. But I can take that tangent, going back 2 slides, I can take that tangent and rewrite it as sine over cosine. So tangent is the same thing as sine over cosine. Do that substitution in green. That one should have been black. And again, I will rewrite that cosine over 1, so it's easy to see that this is a fraction times a fraction. Note that if I have a cosine on the bottom and a cosine on the top, those will cancel, leaving me with just sine on top and the 1 on the bottom. Well, anything divided by 1 is just itself. So what we have here is that tangent times cosine is just sine. So far we've used a reciprocal identity, we've used a couple of quotient identities. Let's mess around with one of those Pythagorean identities. So number 6, notice that we have those squares there. Those squares are your hint that we might want to consider using a Pythagorean identity. So there's usually more than one way to go about one of these problems, but I'm going to take a look at this secant and recognize that we have a Pythagorean identity that's tangent squared of theta plus 1 equals secant squared of theta. Again, there are other things you could have done in this problem. You could have turned secant into 1 over cosine. You could have turned tangent into sine over cosine and then combined those fractions with common denominators. There's always another way to go about one of these. But I'm going to go ahead and just recognize that I have a Pythagorean identity, and so I'm going to use that. So I know that secant is the same as tangent squared plus 1. Pardon, secant squared is the same as tangent squared theta plus 1. And then I still have a minus tangent squared theta. So just because we're playing around with trig, we don't want to forget about our regular old school algebra stuff. I've got a tangent squared of theta and a minus tangent squared of theta. Well, if I'm combining something with its opposite, those cancel. Goodbye. I'm left with a 2, and on the inside of parentheses, I do still have this 1. And 2 times 1, well, that's just 2. So in this case, I was able to simplify down to just a numerical expression. In other words, this giant, ugly trigonometric mess all just equals 2. And that's nice. We'll take a look at one more, and then I'll stop this video, get a second one going. We can't always simplify to something nice. We don't always see something right away that just kind of jumps out at us. Notice that I have a couple of 2's there, a cosine squared and a sine squared. However, the identity that has cosines and sines looks like this. Cosine squared of theta plus sine squared of theta equals 1. Note that those don't match. This one's got a minus and this one's got a plus. Oh no. But the nice thing about an identity is that it's always true. So you can manipulate it if you like. Again, there's always more than one way to go about one of these problems. So what I'm about to do, you might choose to do a different way. But what I'm going to do is subtract sine squared of theta from the identity in order to create a different version. Now I have cosine squared of theta is 1 minus sine squared of theta. You are allowed to manipulate identities because they're always true. So your regular old school algebra methods apply here. I could have subtracted cosine squared of both sides if I really wanted. I could have divided by cosine or divided by sine. There are a lot of things that I could have done here. But what I chose to do is get an identity for cosine squared. I'll do that substitution over here because I have a cosine squared. Cosine squared is now the same as 1 minus sine squared. Oh look, another minus sine squared. So what we have is 1 apple, take away another apple, so that's negative 2 apples or something. 1 minus 2 sine squared theta. Notice that that's not as pretty as the previous three examples, but it is done. We now have just one trigonometric expression. There's nothing else that we can do with that. So that's number 7. I'll go ahead and stop here, and I'll put the next 4 in a new video. See you soon.